Hello everyone. So today let's solve the problem 684 redundant connection. Yeah, let's see what the question states here. This is a simple one basically. Yeah, we are given edges of undirected graph. Yeah, so just give me a second here. We are given the edges of the undirected graph here. Right, see undirected. They have strictly mentioned undirected graph. Right. So see, one edge is 1 comma 2. This one 1 comma 2 or 2 comma 1. Both are same actually. Undirected 1 comma 2 1 comma 3, so this one as well as 2 comma 3, so this one. Yep. So whether it may be 1 comma 2 2 comma 1, or this one 1 comma 3 or 3 comma 1, and 2 comma 3 or 3 comma 2, so these three edges we have, right? So this is fine. We are given edges of the undirected graph that started as a tree of n nodes, that started as a tree of n nodes with exactly one extra edge added, with exactly one extra edge added. Yeah. So with this one, with exactly one extra edge added, we have to return the edge. We have to return the edge whose removal makes the graph a tree again. Whose removal makes the graph tree again. Right. So if multiple valid answers exist, then we have to return the one that appears last in the input. That appears last in the input. See here, removing 2 comma 3. So suppose if we remove this one, 2 comma 3 actually. So this edge actually, basically what happens, we will be left with 1 2 as well as 1 3 actually, 1 2 as well as 1 3. This forms a tree, right? So this is fine. Yeah, accordingly with the question, we are given edges of the undirected graph that started as a tree of n nodes, right, with exactly one extra edge that has been added. We have to return the edge whose removal makes the graph a tree again actually. So removing this one doesn't matter actually, we still have all the edges, right? So we have one extra edge, nothing but 2 comma 3. So this one, if we remove this one entirely, we are left with only 1 2 and 3. So this one actually, we have still 1 2 and 3, meaning we have all the nodes 1 2 as well as the 3, right? So this is fine. So this one we have to return this one as the output. Yeah, very simple. Yeah, let's move on with the second example, man. Here, so let's move on with the second one here. So we have 2 1 5, so basically 3 4. So this is also the undirected graph. There's, see here, 1 to 2 is one edge, 1 to 5, or next 2 to 3 they have mentioned. Let's go with the same thing that they have mentioned here. 2 to 3, this is also one of the edge. 3 to 4, so yeah, this is also one of the edge. And 1 to 4, this is also one of the edge. So this is fine. Finally we have 1 comma 5 or 5 comma 1, the last one. Yeah, so this is fine. So see here, so removing one edge, still we should have all the nodes. In simple terms, still removing that edge, that should form a tree with all the nodes. Yeah. So here in this case, we will be removing 1 comma 4, this particular edge, right? So we will be removing a 1 comma 4 here, this one. So we are left with 1 to 2 here, 1 to 2 actually. Yeah. 2 to 3 we have, 2 to 3 we have. This is also fine. 2 to 3 we have. 3 to 4 we have, 3 to 4 we have. This is also fine. Yep. So in this order also you can write, or let me write it in this way itself. So we will be having 1 to 2, right? So let me write it in this way itself. So let me take the right, this one at right. So this is fine. 2 to 3, 2 to 3. So this is also fine. 2 to 3, we are left with 2 to 3. 3 to 4, we have 3 to 4. Again, we'll be left with 3 to 4. Finally, we have 1 to 5, actually 1 to 5. So removing this particular edge 1 to 4, still it forms a tree with all the nodes. Still it forms a tree with all the nodes. So removing this one, we have to remove the edge 1 comma 4 here in this case. Simple one. Yeah, let me remove this one. So yeah, they have given us wonderful examples, right? Just for the sake of understanding. So now let's do one thing. Let's quickly discuss the this one approach followed by the complexities, and then let's write the code, man. Yeah. So approach here. So let's go with the disjoint set union. So basically what we'll be doing in the DSU, or the this one union find, disjoint set union, or the union find basically, right? So we will be making use of the two functions actually, two helper methods when it comes to Java. So one is union and another one is find. So within the find, what we will be doing basically, within the find, usually we'll find the representative or the parent or the root, along with the path compression. Yeah. So that's the faster one, right? And also union, in the union helper method, or the function, usually what we do, we will go by union by rank actually. Based, it may be based on size. Usually we call this one as union by. So usually we'll be going with union by rank actually. Yeah. So these two things. If you know the union find algorithm, it's very easy to implement. Yeah. So if you don't know union find algorithm itself, you can just go through the this one graph based playlist. Again, you can just go through the this one. Go to the graph based playlist and you'll find the union find or the disjoint set union algorithm. You can just watch that one and come back. Yeah, it's very easy, very simple one, man. Yep. Now let's move on with the approach part. So the first part here would be, let's consider the same first example for the approach. Yeah. So the first part, let's make use of the disjoint set union or the union find to track the connected components as we process the edges in the input order. As we process the edges in the input order. So this is the first point actually. For each edge, sorry, for each edge u comma v, for each edge u comma v, if find of u is equivalent to the find of v. So this one will be going with within the find this one helper method, right? If find of u, if it is equivalent to the find of v. Let me write this one over here, right? So I'll just write here find of u equals find of v. Then adding u comma v would form a cycle. Then adding u comma v would form a cycle, right? So adding u comma v forms a cycle. You would have already guessed the further things, right? So the edge is candidate to remove. So we shouldn't, it shouldn't form the cycle. If it forms a cycle, it's irrelevant. It's the extra edge basically, right? So in that case, what we have to do, so this edge is candidate to remove basically, because we must return the last such candidate, keep updating the answer whenever we detect a cycle. Otherwise, union of u comma v to merge the components. Yeah. So this is simple, man. This is simple. That's what we have to do. For the particular example that we have considered here, we have 1 comma 2, 1 comma 3 and 2 comma 3. Yep. So first what we will do, we will process 1 comma 2 here. We will process 1 comma 2. So 1 and 2 are separate here. 1 and 2 are separate on the node. 1 and 2 are separate here. What we will do, we will union them. So we will union them. Yeah. So next what we will do, we will consider 1 comma 3 actually. 1 comma 3. What we'll do, 1 and 3 are separate. Then again, we will union them. We will union them. So this is fine. The final one we have here is 2 comma 3. We have here is 2 comma 3. So find of 2 equals find of 3. Find of 2 equals find of 3. So this would form a cycle. So we already have 2, we already have 3 here. Find of 2 equals find of 3. So this would quite obviously form a cycle. So what we do, we record this 2 comma 3. No more edges we have, right? So we'll do, what we'll do, we will return 2 comma 3 here. So we will return this. Will return this 2 comma 3. Yeah, as this forms the cycle. Yep, no more edges are left. So we don't have to worry about the further step. So this one we will return actually 2 comma 3. Yeah. So 2 comma 3 will return this one as the output. The output that we got here is 2 comma 3, which is equivalent to the output that they have mentioned for the example one within the question. Yeah. So our approach works absolutely correct here. So as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part. So what will be the time complexity and the space complexity here? First of all, what will be the time complexity? So time complexity is big of n. So why it is big of n here? Sorry, why it is big of n here? Yep. So it's basically big of n into an actually, right? So this one, inverse Ackermann, the small value a of n, n into a of n, right? So it is almost equivalent to n actually. Let's consider big of n directly. Yep. So it's the time complexity would lead to big of n, where a is nothing but this one, a that I said, right? So we can just write it in this way as well, big of n into Ackermann of this one. Yeah, this is also fine, where a is nothing but the Ackermann inverse, this one inverse Ackermann. We do find our union for each edge, right? So overall time complexity would lead to big of n, or you can just consider this one if you need precise one. Yep. So this is also fine. What would be the space complexity? Space complexity of the space complexity would lead to big of n as well, because we'll be making use of the parent and rank arrays. Yeah. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n and big of n respectively. Now, as we are completely familiar with the approach and the complexities part, we are good to write the code. Let's start writing the code. Yeah. So the first step here would be, let's go with the parent and the rank arrays for the DSU or the disjoint set union as discussed. Just now we discussed the same thing, right? So within the complexities part. So I'll just go with here, sorry, and parent. So this is fine. So let's go with the rank of I, nothing but it's approximately this one tree height for the union by rank. So I'll just go with here private. This one will be int rank. Yep. So this is fine. The next part would be let's go with a this one. What do we call? So I'll do one thing. Let me remove this one. Yeah, yeah. Remove this global as I've made use of the private. Yeah. So yep. Let's do one thing. So within this main function actually, or the main yeah main method actually, find redundant connection. So we have the parameter edges, right? First, let's do one thing. Let's go with the number of adjustment. Number of edges has to be equivalent to the number of nodes here. So this one will be int n equals edges dot length. And the next one is let's go with the parent. So let me assign this one to the new int of size n plus 1. Yep. So this is also fine. The next one would be let's go with the rank here. So this one again, let's assign this one to the new int of size n plus 1, assign or initialize this one. This is fine. Next step, let's initialize each node as its own parent. So let's move on with the iteration part here. Int I equals 0, I less than or equal to n. So let me increment the I. So this is fine. So I'll just go with the parent of I that is equivalent to the I, right? So this is fine. Uh, let's go with the resulting variable, anything, just to store the last edge that forms a cycle actually. Just now we considered the first example that I showed, right? So how we will be making use of the union as well as the find. Yeah, so this one will be int resulting variable. I'll go with the answer. N is here. New int of size. I'll just go with the 8. So 2 edges. So we only need 2, right? So I'll just go with the 2. Basically edges, right? So now let's move on with the iteration part. I'll just go with for int I equals 0. I less than just dot length I plus plus. So this is fine. So now within the for loop, first let's extract this one, extract the first endpoint, and also let's extract the second endpoint, right? So this one will be int u equals edges of I as well as the 0. Yep. Also int v equals edges of this one. What do we call? I and 1 respectively. So this is also fine. I forgot on the semicolon here. Let me include semicolon or else we'll be getting the error. Yep. So the next part, let's go with the find actually. So before making use of the find and union, let's do one thing. Let's write the helper method, this one. What do we call? Find as well as the union. Find is used to basically what we'll be doing. Find is used to find the representative or the parent or the root, right? Find with a path compression usually. We call this one find with path compression. Yeah. So let's do one thing. Let me go with here. Sorry. Yeah, private, and let me go with a find. So here we need one parameter x if you know the algo. So within the find helper method, so I'll just go with if parent of x we have to consider, right? Parent of x. Um, if it is not equal to x actually, then what we will do? Let's go with the parent of x. Let's go with the find of actually parent of this one x actually. So this is fine, I believe. Yeah, we are just compressing the path. We are going with the path compression itself, right? So finally, we'll return the representative or the parent or the this one root actually. So I'll just go with return parent of x. This is fine. Yep. So let me come out of this one entirely. Now let's go with union by rank actually. Another helper method, union here. Private. 1 second. Point. Yeah, I'll just go with the union. So let me go with int a comma int b. Yeah, these are the parameters that I want. A equals, let me make use of the find. A equals find of a as well as b equals find of b. Simple. Yeah, simple. Next, we are just going with a representative of A and representative of B, nothing but the parent of A and B. Next, what we are doing, so if both are already in the same set, I have shown you then this one actually in the algorithm. If you don't know, again I'm telling, if you don't know disjoint set union algorithm or the union find algo, just go to the graph algorithms playlist and you can just find the algorithm there. Just watch the video and come back, right? So it's in the programming language Python, so you'll understand approach is exactly same. Yeah. So if already A and B are already in the same set, then we have nothing to do, right? So we have to exit from there. Yep. So I'll just go with if A equals B, right? So I'll just give here a return. Yep. So this is fine. Next, let's go with a simple if condition. If mm, rank of if rank of actually A less than rank of B actually, then what we will do, so within the if condition, I'll just go with the parent of A. Let me assign this one to the B, so this is fine. Else, if what we will do, rank of this one, what do we call A, if it is greater than the rank of B, then what we will do, so let me go with the parent of B actually. Let me assign this one to the A, right? So then finally, let's go with the else here. Else what we will do, so parent of B, let's assign this one to the A actually. B, let me assign this one to the A, and finally, let's increment the rank of A here. Yep. So this is fine, man. Yeah. So what I have written here, if a rank of A less than rank of B in the sense, so we are just attaching the smaller rank tree under bigger one, right? So we are just attaching the smaller rank tree under the bigger one. So the next one, else if whatever I have written here, this one parent of B equals A. So we are just attaching the smaller rank tree under bigger again, right? Smaller rank tree under bigger one again. So finally, if it is a tie, if both have the same value, then we will attach B under A and increase the rank of A. So that's why we are this one incrementing here, right? So this is fine, I believe. So let me format the code once so that this looks good. So this is fine. So now we can just make use of the this one. What do we call? Find and union within the main method actually. Yep. So I'll just come here where we have left. So yeah, now let me write the simple if condition here. If find of u, if it is equivalent to the find of v actually, find of v, then what we need to do actually, what we need to do, so here u and v are already connected. This edge would form a cycle quite obviously. So this one, answer of zero, answer of zero, let me assign this one to the u actually. So this is fine. And answer of one, this one, let me assign this one to the b. Yeah. So next what we will do, I'll just go with else let me call the union function here or union method. So let me pass u and v here, right? So otherwise we have to merge their components, right? So here we are recording as candidate. We are just keeping the last. U and V are already connected. This edge would form a cycle. We are just recording as candidate. We keep last, right? So here, otherwise, this one else union of U comma V, whatever I have written. Otherwise, we have to merge their components here. Finally, we are left with only one step actually. Y space here. So this is fine. So let me do one thing. Now, finally, we have to return the last recorded cyclic edge, right? So I'll just go with return answer. This will be stored in the answer variable. So let me return the answer ANS actually. Yep. So let me hit the run button. I hope this works, man. This has to. Let's see. Yep. The sample test cases are getting passed. So let me hit the submit button quickly. So this is simple, man. This is fine. Yeah. Yeah, all the test cases are getting passed here, right? So whatever the code that we have written works absolutely correct for all the test cases, right? I hope the solution part is completely clear along with the approach and the complexities part, right? So for now, this is it. Thanks for watching, guys.